When you are working a 3D equilibrium particle problem, it's very similar to what you did in 2D particle equilibrium, except we just have an extra equation. So in 2D particle equilibrium, we had the sum of the forces in the x are equal to 0, and we had the sum of the forces in the y are equal to 0. Now when we're working 3D problems, all we do is we add in an extra equation. We have the sum of the forces in the z direction are equal to 0, and these are the three equations we are going to use for particles. Now, if you're working with rigid bodies, there's a couple of other equations that you can use so you can solve for more unknowns. The most that we can solve for with these equations, we have three equations, we can solve for three unknowns. Now, if we look at this problem here, what we have is we have this 100 kilogram weight that's being supported by three cables. One of these cables is this cable right here, this cable AB. One cable is AC, and those are along the X and Y axis respectively. The other cable that we have is this cable AD, and this is a cable in 3D space. Now, as soon as you see a cable or a force in 3D space, you want to express it as a 3D Cartesian vector, so you don't need to worry about geometry or trigonometry or getting any of your angles wrong. If something's along an axis, that's very easy. It just has whatever that axis component is. So for X, that's an I. For Y, that's a J. And for Z, that's a K. If you're in 2D, which this problem doesn't have, you can use a lot of your triangle relationships to decompose that and resolve that along the appropriate 2D coordinates. Now, the first thing you need to do on any of these problems is draw a free body diagram. I'm going to start here with my weight. My weight points downward, and my weight is going to be equal to this 100 kilograms times gravity, which is 9.81. And so this gives me a weight of 981 newtons. Now let's look at each of these forces. I know they are cables, so they're going to all point away from A. So this AB points along X, and we'll call this TAB. This force AC points in the minus Y direction. So this is going to be a force TAC. And this AD is in 3D space, and it points away from A. And let's write all of this as Cartesian vectors. So let's start with TAB. TAB is going to be equal to TAB, the magnitude, times I. If we look at TAC, TAC is going to be equal to the magnitude TAC times J. And we have to remember this is pointing in that minus direction. So it's going to be minus TAC times J. And then I'm just going to write my weight here. So my weight is pointing in this minus Z direction. So it's going to be minus 981 K. And now we just have to work with this force TAD. It's in 3D. So what that means is we need the location of A. A is at 0, 0, 0, right? It's right at the origin. And we need the location of D. D is at a location of minus 2x, 2y, 1z. So minus 2, 2, 1. Now, this is a force along a line. So when we remember what the force of an equation along a line is, we have already here the force is equal to whatever the magnitude of that force is times a position vector over the magnitude of that position vector. For us, our force is going to be this unknown force TAD. The position vector is going to be the position vector from A to D, and the magnitude is going to be whatever that magnitude is. So let's figure out what this position vector A to D is equal to. And we're going to start at the head of the arrow, and we are going to go to the tail of the arrow. So this is going to be minus 2 minus 0 I plus 2 minus 0 j plus 1 minus 0 k. And if I simplify that, I get minus 2i plus 2j plus 1k. And the magnitude of this is going to be equal to the square root of each of these terms. So this minus 2 squared, which is 4, plus 2 squared, which is 4, plus 1 squared, which is 1. So this is square root of 9, and this is equal to 3. So let's write this equation. This TAD is going to be equal to TAD times this position vector minus 2i plus 2j plus 1k all over 3. And we can simplify this again. We can say, okay, this is equal to minus 0.667 TAD I plus 0.667 TADJ plus 0.333 TADK. And now we have all of our vectors. The next step, what we need to do is we need to use our equations of equilibrium. These three equations that we have right here. So let's start with the sum of the forces in the x. When we start with the sum of the forces in the x are equal to 0, we need anything with an I. So here we're going to have TAB, and we're going to have minus 0.667 TAD is equal to 0. Two equations, two unknowns, only one equation. So we need to keep going. Let's go to the sum of the forces in the y, which is equal to 0. Okay, now we need anything with a j. So we're going to have minus TAC, and we're going to have plus 0.667 TAD is equal to 0. Again, now we have 1, we have 2, we have 3 unknowns, and we only have 2 equations, so we need to keep going. And we're going to go to the sum of the forces in this z direction, which is equal to 0. Now this z direction, what do we have? We need the k's. So we're going to have this minus 981. So we're going to have minus 981. And in this equation, we have this 0.333. So plus 0.333 TAD is equal to 0. And what you're going to see is now in this problem, we can solve for TAD. We can bring this, we can say 0.333 TAD is equal to 981. And we can have TAD is going to be equal to 981 divided by 0.333. And this is equal to, let's do that calculation. 981 divided by 0.333. 2,946. So this is 2,946 newtons. Okay. But now we have an expression for TAD, and we can substitute it into both of these equations. We can go back to the sum of the forces in the y and the sum of the forces in the x. Let's go back to the sum of the forces in the x, and we'll have TAB is equal to 0.667 times 2,946. And this is going to be equal to 0.667 times 2,946. This is equal to, I'll just write it below, TAB equals 1,964 newtons. And finally, we can go to this TAC. Let's solve for TAC, bring that to the other side of the equation, and that's going to be equal to 0.667 times 2,946. And this is going to be equal to the same thing. It's going to be equal to this 1,964. 1,965. Let's be consistent with how I rounded. And this makes sense in terms of magnitude. They're all pointing away. They are all ropes. So we don't expect the having to switch these directions. So these are the forces that are developed in all of these ropes.